Hello everyone, and I'm Michael Liu. I am currently a graduate student at MIT, and I study on-orbit servicing for my research. And as we've firmly established, on-orbit servicing is, I'm already talked to the audience that is most concerned about the topic itself. Well, for the audience here, let's review, as previously mentioned in the previous section by that on-orbit servicing in GEOs is sort of been established with the mission extension vehicle from Northrop Grumman. So the servicing case in geosynchronous orbit has been firmly established. Geosynchronous satellites tend to be more monolithic, much longer lifespans, design lives, have much more robust sensors, and therefore are quite exquisite in their payloads. So it makes much more sense from a cost value perspective to service those assets because you would just get so much more utility in terms of extending that investment. Now, the question as we shift in terms of an industry towards low Earth orbit and proliferated constellations or mega constellations, does on-orbit servicing make sense? LEO design lives are much shorter. Those payloads are much cheaper, easily replaceable, and the constellations themselves are designed to be distributed and disaggregated to the point where does it make sense to replace them, particularly with low-cost ride shares and insertion into LEO. So this is an overview of some of the concepts in terms of servicing in low Earth orbit. And on the left here in the blue that's highlighted, we have a traditional concept of operation, which is that you launch a satellite, a servicer, a spacecraft with all of its resources on board that it carries as inert mass throughout the mission profile to visit various targets. You wouldn't visit just a single target or a single node because pretty much you could just launch a replacement satellite for that object. So with that, you do have a significant penalty in inert mass and propulsion as you carry that servicing resource throughout the mission profile. And the secondary concept that has been reviewed quite extensively are the use of depots. And depots now provide a significant advantage in terms of waypoint and resource and logistics. However, you do have to travel back and forth from that depot, and thus there is some overhead in terms of your resources that aren't directly contributing directly towards reaching a client or imparting some of your mass or energy into the client or target system. So a concept that I've looked to adapt, which was motivated by Northrop Grumman's proposal to use the next step forward in their mission extension line, which is the mission extension pods, which they proposed in GEO, is to deploy a electrically propulsed servicing pod, which pretty much provides station keeping and basic guidance and control in terms of electric propulsion to get in the vicinity of a target satellite. Now, that pod doesn't have the visual recognition or the control authority in order to perform a rendezvous and dock with a target satellite. That servicing requirement is pretty robust, and if it's only going to be used once, then it relies on the servicer to rendezvous with that pod, capture it, and then use the servicer's systems in terms of robotic manipulation and visual recognition and chemical propulsion in order to execute the actual rendezvous. And then it robotically attaches the pod to the client spacecraft and then moves on to the next target, to the next pod, and execute the same steps over again. So that has been explored in GEO and is currently proposed. There hasn't been too much research or literature on it. However, I'm looking to adapt that into a low Earth orbit analysis. So there you can see it in the green on the right, the pod count. So with the environmental considerations, we know that maneuvering in GEO is quite advantageous from an energy perspective. You have a lot of time to raise yourself and to conduct a coplanar maneuver from an in-plane and out-of-phase conjunction maneuver, which is more efficient as you escape Earth's gravity well. However, when you're so close to the Earth in such low Earth orbit, you're facing a lot of other environmental factors. J2 is a significant one, as well as drag. And as we know, direct plane changes are very cost prohibitive. So with these mega constellations, proliferated constellations, you do have sort of what they typically have are either multiple shells and or if not multiple, they always typically have a static inclination duplicated over multiple RANs or RAN separations between those phases. Here you can sort of see that's an overlay of Iridium on the left-hand side, which has the most empirical data we have for a low Earth orbit proliferated constellation. And that's sort of what this analysis is run on. However, I wanted to make this as scalable as possible because doing an optimization for a particular satellite would confine you to an explicit solution, but it necessarily wouldn't allow an on-orbit service satellite provider to service multiple clients or a heterogeneous mix of satellites. So this is meant to be a generalized and scalable solution. So on the left, I actually utilize the J2 perturbation as leverage to not execute an out-of-plane maneuver. What I do is I use a Hohmann transfer to execute an altitude lowering, which as a function of nodal precession, as you can see here, is a function of yes, your inclination. So polar orbits, it doesn't really affect as much. But as you reach that 68-degree-ish inclination, which a lot of satellites constellations are doing, it's a huge function of altitude. So you want to get from your flying altitude as much of a difference from your flying altitude as possible to execute a westward drift of nodal precession in a prograde orbit to align to your next RAN. So that's your next plane. And then for changing your true anomaly for within the same plane, it's a synchronous maneuver. The same thing as a subsynchronous maneuver where you lower your altitude to a phasing orbit, allow for that delta in period to occur, and then you raise your orbit again. Now, the problem with rendezvousing, there's a set integer, which is I specified as the number n here, which is the division of the time per in-plane maneuver, which is divided by the period minus the phasing ratio, plus 1. So that is a derivation I've made to execute either a chemical or electric repulsed maneuver to phase your true anomaly in an in-plane maneuver in a scalable way where you can adjust the time you want to take. So it's a trade-off between time and energy in terms of delta V and how quick you want to execute this maneuver. So just how much are you going to spend in terms of executing these maneuvers? So I did a trade analysis with these specifications regarding an on-orbit servicer with that dry mass and that ISP at this particular flying altitude. And what we can see is that if you were going to maneuver, this is just the delta V on the left and the mass on the right. Basically, if you're servicing and want to do it in an expedited manner, so either in emergency or exigent circumstances, you're going to pay a huge penalty in mass, right? Because the delta V equation, it's exponential. So if you want to transfer nearly within, sub 1 day, you're going to pay a huge delta V penalty. However, if you're more patient and you're willing to not go to so low of a phasing altitude and willing to wait in your phasing period a little bit longer, you can save substantial delta V and propellant mass. That should be relatively obvious, but using that in conjunction with a pod CONOP versus traditional mission CONOP, this is an analysis here that looks at the mass and cost difference between the two. Now, the blue line on top and the gray line on the bottom, those are the masses, and then the red line in the middle and the orange line in the middle there, those are the costs comparing the traditional and pod CONOPs. Now, basically what this is you get exponentially more savings in terms of cost as well as propellant mass by implementing a pod CONOP for this sort of phasing, for this sort of scope of maneuver. So the pod CONOP is much more economical. So I'm going to focus on the pod CONOP. I think that for this particular analysis. And now let's look at what are those sensitivities for designing the style of servicing that would also affect the system requirements on an on-orbit servicer in terms of altitude and time and masses. So the ones I particularly focused on here, the effect of client altitudes. So I looked at a variety of client altitudes in LEO. So that's going to include 500, 4 altitude regimes, pretty much equally spaced, 500, 750, 1,000, and 1,500 kilometers. And looking at how your client's altitude affects the on-orbit servicer, but also how fast you want to service. So as we know, your cost and delta V requirements are a function of how much lower in altitude you go. So on the left, there's a static case of lowering your altitude 125 kilometers statically from your client altitude to your servicing and phasing altitudes. And on the right, you have it as a percent of your client's altitude. So obviously, as you go to 1,500 kilometers, 25% of your client's altitude is going to be substantially more than it would be at 500 kilometers. And what this shows is that the client altitude, servicing as a percentage of your client's altitude, is significantly favored at lower altitude regimes. And you get substantial mass savings, though, if you go statically just a few kilometers below. But what's the cost? And the cost is obviously time. And so here, the inverse happens, where you pay a huge time penalty depending on your servicing, about how long you're willing to service. Now, excuse me, this can come into play. So this is largely an effect for what is your servicing style going to be? Is it going to be on demand, or is it going to be scheduled? Now, a scheduling service is highly predictable, and we're able to size and scope our servicers accordingly to the mission profile. However, if your service is going to be up and you're looking for more clients and you're going to look for more altitudes, then you have to, this provides the sensitivities in the analysis in terms of building a framework to understand, well, what cost and what's my margin, and basically what are those reach targets and what are our feasible targets. Now, we see here that basically the inverse relationship from mass, which is going to be the time you take to get there. So a huge amount of time, but what we can see here consistently that I'll highlight are the number of planes along the x-axis. So for both servicing regimes, whether you are being very prudent and frugal and going just a small portion below your client altitude, or you're making, servicing higher altitude clients, which are more exquisite and willing to spend more servicing resources to reach them and service them in a timely, efficient manner, you have economies of scale. So at higher number of clients and planes, as you get more proliferated, on-orbit servicing becomes much more effective as the scale increases, particularly with pods, because you're not being taxed in your inert mass. The pods are scalable; they can deploy on separate launches, on demand, and phase throughout the mission profile. So these are the effects of client altitudes. We can see here that there's a large delta in terms of the number of planes that the client occupies. So if there's a single plane, obviously it's very expensive in terms of the time taken to get there, but the difference in time between each target greatly decreases as the constellation becomes more proliferated. Now we can see there's only a few days of separations between reaching your subsequent clients. And now that can obviously scale not just with pods, but you can add more servicers into the constellation to insert into more planes. So the cost model. Now the cost model does present some difficulties because we don't have a good model yet in terms of a high serial production amount of satellites outside of Iridium for low Earth orbit, right? These are mostly, so the servicer itself was derived from NASA's upcoming OSAM-1 mission, which is a low Earth orbit robotic servicer, and I scale that based off the mass. Launch costs are considered. It's a linearization of a Falcon Heavy SpaceX rideshare to LEO because they're launching so frequently, and so there's two cost models I sort of took into perspective, which is a high cost model for low serial production for any satellites from 1 to 11, mostly based off those stated satellites there, and then a low cost model, which takes into account this sort of projected cost of these next generation satellites, also sort of tempered with the cost of Iridium satellites. Now, I will caveat that the Starlink quote of satellites I have, which is very, very exotic, which is they're saying that it's, well, exotic in the scheme of their quoted economies of scale, saying that they could possibly get sub $300,000 a satellite, which is maybe not feasible. I would probably assume somewhere in the $1 million range. So it's very biased and giving the benefit of a doubt to a very disposable, very low cost satellite. That's what I would say. So basically, this is sort of the summary slide, which is that for high cost replacement satellites, it makes a lot of sense to service the high cost model satellites. In terms of the low cost satellite model, it depends. It depends on the client altitude. It depends on the cost of the client. These curves for the low cost model are very low, as I said, because I'm giving the benefit of the doubt to the client satellites that they'd be a lot cheaper than they are. And so this helps build a framework for the analysis that should go into a low Earth orbit constellation, and pretty much cost effective up to everything, particularly at 750 kilometers and above, as you escape the gravity well. But you do need to be, it is highly sensitive to the altitudes your client is and how fast you want to get to each target. So this is the summary slide, pretty much re-encapsulating everything that I've stated so far. I will say that for the ongoing well, actually, I'll just recap this. The main point I want to take away here is that there's a lot of sensitivities in a low Earth orbit on-orbit servicing constellation design. It's highly advantageous and scalable, and a conceived future step forward are that sort of, government investment or sponsorship or risk mitigation in terms of development technology demonstration, and then a shift towards commercial providers as they can adopt on those gains as a benefit to the space community and industry and policy. And the future work coming from here, which is all the analysis that you've seen so far was on chemical propulsion on a monopropellant hydrazine type system. And the future model that I'm working on in the next set of publications that I plan to publish are going to be a combination look at electric propulsion, which there are feasible solutions in low Earth orbit in terms of electrical propulsion and on-orbit servicing. Obviously, as you become more biased towards being time agnostic, that becomes even more advantageous. And it depends on the sensitivity of how sensitive you are to your time. And looking at an enumerated trade space for looking at more proliferated constellations above that 80 satellite constellation range that we've seen here. What happens when you look into thousands of satellite scales and multiple shells in that scheme? So that summarizes that, and I will end on that note. And I think we have the panel discussion coming after this.
Okay, thank you very much. So we don't have a lot of questions actually. So if you want to ask your question, please feel free to put it into the chat now. We can start with one for Michael Liu. So one question would be, have you considered other concepts of operations? How have you considered to look at the pods concept specifically?
I'm sorry, you said how would I look at how, sorry, can you say your question again?
So have you looked at other types of concepts of operations, or how have you decided to look at the pods concept for your study?
So originally I did start off with sort of a traditional concept of operation, which is carrying the traditional flight, sending a single servicer up and visiting multiple targets. And looking at that, the margins were very slim and the performance was was pretty hard to get. You had to spend an enormous amount of time in orbit, which would exceed the design life of your target constellation. It's possible to do it in emergency and exigent. So if you have a high value or something very drastic, you can service in that scheme. The other ones we did look at were depots, but as I started to integrate depots within the system, as previous speakers had stated, you get sort of NP hard traveling salesman and optimization and sort of explicit discrete solution focus. And I wanted to look at something much more discrete. And not only that, I wanted to look at, so something else I'm also doing in my future work is looking at different schemes of servicing, and not just replenishment of delta V and propellant, but looking at inspection, upgrade, replacement, and heavy maintenance in terms of replacing components or payloads and sensors on satellites. And so that's what drew me towards this sort of concept, because I can normalize for different servicing resources and payloads and things I want to install or implement into the system. So yeah.
Thank you. Okay, I'm just looking at other questions. So I think this one is also for Michael. Maybe this was said implicitly. Roughly how many service targets in LEO are needed to make a servicing mission worthwhile? Maybe it depends.
Yeah.
What's the range?
So it does depend. And so let me just highlight this, maybe this slide again. I can go ahead and just share this, which is looking at this for if your serial satellite production is below 11. Now this is a big mix, right? Like you could be servicing, the question is, are you servicing all the same satellites and they all valued at the same thing? So if so, and there's below 11, then I postulate that yes, anything, you shouldn't service 1 or 2 or 3 satellites. That probably isn't worthwhile. However, if they're even in the LEO spectrum in a high cost model, yeah, you could service them to extend their lifetime. That makes sense. So it's sort of like a duality paradox almost, where you're saying, oh, if there's not that many satellites to service, you don't get economies of scale. However, if you have a homogeneous constellation and you have anything that was produced in low serial production, it was probably an exquisite satellite. So you should service them. But if you have a proliferated constellation, you sort of get this bend in the curve where it makes sense to service a lot of those. So it's highly flexible. So I don't think it's dependent on the number of satellites. It's more of how much does your satellite cost and how fast do you want it to be serviced. I don't think you can service on demand too much in LEO. As long as it's scheduled and forecasted, it's feasible.
Another question is, how about other regions else than LEO?
So within outside regimes, if you're talking about highly inclined like Molniya orbits or something like that, which goes into which is another benefit, right? On-orbit service can allow you to reduce your system requirements in terms of like radiation shielding or resilience in terms of your satellite, and then you could theoretically service and replace those and be willing to risk these non-occupied orbits that aren't as popular. Servicing multiple planes in that orbit presents a different challenge, a new challenge, because these orbits are largely circularized. So I haven't really looked at these highly elliptical orbits. GEO makes sense that people are already targeting GEO. I already know that people are already out there, as we said, Northrop Grumman and RSGS and so many other programs that are looking to service GEO satellites. Lockheed Martin just announced they're making their next block of GPS satellites serviceable with interfaces. So I think polar orbits do present a unique problem because I can't use J2 in highly polar orbits. But a lot of the new proposed constellations in terms of Starlink and things like that are roughly inclined at about 68 degrees. You get a good advantage of J2 around 68, 65 degrees, right around, not completely equatorial, not polar. So that's the most advantageous. You do get a decreased advantage as you move towards more equatorial or more polar orbits. So I hope that answers that question in terms of other regions. But I think it would be pretty unique to see what would happen if you started entering the Van Allen radiation belt, like could you theoretically assume more risk by reducing by accepting some sort of degradation, but your ability to influence and fix those satellites? Very unique possibility. I think that opens the window quite a bit, but I don't have an answer for that just yet.
Were you able to find an upper stage that supports your pod ConOps?
An upper stage. I'm not sure what you meant by upper stage, like upper stage propulsion or upper stage. Yeah, Sungwook, if Sungpak, if you could clarify maybe what you mean by upper stage, like upper stage of an upper stage deployer. Huh, I'm not sure. So an upper stage deployer. I'm not sure what you mean by an upper stage deployer. Upper stage deployer. I'm not sure whether you're referring to the pods that get released in.
Yes, I think this is a question about the pods and how they're released and whether this.
The pods and how they're released.
Yeah.
So the pods and how they're released. They typically take. You're going to have to do a lot of forecasting in terms of the pods. So the pods obviously are going to be. They're very small. Most of their mass is going to be inert mass that you're trying to reserve a lot for the target satellite. So they take months to raise. So looking at that, we looked at sort of just a Hall effect thruster that does have a beta value. There's an optimal sorts of. So your limitation isn't on the forced production of a Hall effect thruster, because we typically have those efficiencies and we can get a decent amount of thrust with the ongoing research. You're really limited by the size of your solar array. So there's a beta value and efficiency threshold that you reach in terms of how, and that's going to be your backwards planning factor for when you need that thing to be in target at a certain altitude. So yeah, your orbital insertion will range, and how far that thing needs to phase either true anomaly in plane or to a different plane. You just need, it's on the scale of weeks to months of forecasting and planning to get pods out there. So that's sort of assumed that with this servicing ConOp, you definitely need to have a lot of forecasting. Yeah, I hope that answers the question. Yeah, I don't want to monopolize time. If you want to get to, I see another question there from Gabriel. Basically, I'm not discussing standard connectors. I know a lot of people are. Confers, which is the consortium for interfaces, is working on that. I know Astroscale has theirs. So this is sort of, that is not the, I'm not really focused on the interfacing component. I do know that we can phase and sync with apogee kick motors on most satellite constellations. We've sort of proven that out with non-intended servicing interfaces, but that's sort of assumed out of this research. Thanks.